Hello everyone. I want to welcome everyone to this section of my video, and I want to implore everyone that is watching my video to kindly like my page and follow the page for more information in case of when I release some of my articles and some of my blog papers so that you can follow. This section of my video will be directed and channeled to stemming operation and stemming length control and its effect on blasting. So I will start by explaining some of the terms like stemming and the old length and some of the terms that I'll be using in case of those people that are not in mining department that doesn't have any connection with mining to have understanding. Stemming or what is called collar distance or collar length is defined as the section of the section of the hole that is left after charging, the distance from the charging point where the explosive level get to the surface. So the distance, the vertical distance from the level of the explosive charge point to the collar point is what we call the polar distance. So stemming is directly defined as the process of using an inert material in the place of the drill cuttings and the place of aggregate of materials of size ranging from 1 over 10 of diameter to 1 over 20 of diameter of the hole to fill in the space that is left after loading the explosives so as to confine the hole. So stemming is merely done to confine the explosive energy within the hole so as to avoid improper or accurate distribution of explosive energy detonation. So as I've defined earlier, that stemming is the process of using inert material to confine the explosive charge within the hole so as to ensure accurate and perfect distribution of energy during detonation. So what are those things that controls the length of stemming? One of those things that control the length of stemming that to be abandoned or leave behind for the infilling of inert material is the strength of the rock and the nature of the rock. In the place of the strength of the rock have to do with the property of the rock. Rocks are of soft and of hard strength have various challenges in the place of stemming. So rock that of higher strength require high and long explosive length or explosive charge column. So therefore, thanks to vary the stemming length compared to that of soft rock. So other properties, the strength of the explosive, the rate, the quantity of energy released by the explosive, and other parameters that affect stemming length is the burden and the spacing, the bench height, and the place of the hole diameter. The hole diameter has high effect on stemming. In most of the scholars that have worked and research on stemming, they tend to conclude that stemming tends to be 10 to 20 of the hole diameter, while in terms of related to burden, it tends to be is 0.7, is 0.6, is 0.75, 0.8 of the burden. So to calculate the stemming length, the length of the hole that will be left behind to fill with inert material, it's calculated to be 0.7 of the burden, that is the burden that is abandoned, the distance from the first row of the holes to the free face. So it will be of 0.7 of that distance for the stemming. So how does stemming affect blasting? That is what the video will be channeled to. How does stemming affect blasting? One thing that I want us to understand, whether you're a blastomer or you are an engineer, is that when it comes to the transfer or distribution of explosive energy within the hole, explosive compressive strength that is released as a shock wave tends to travel faster within the rock than traveling within the stemming distance. What I'm trying to say is that as soon as the explosive energy is released in the place of compressive strength or shock wave that's supposed to do the microfracture, it tends to travel through inert material faster, intact material faster in the place of the rock mass. So it travels faster within the rock mass compared to the speed at which it will travel within the stem length. So the blasting stemming length is to be designed in such a way that the time that it will take the shock wave or the compressive energy to travel from the blast point to the free phase return to create tensile slabbing must be greater than the time at which the explosive energy will travel through the STEMI column. So we understand that when the explosive energy is released, it tends to look for the place that is having lex burden. In such case, if the STEMI length is low or is very small compared to the burden in the place of the distance between the burden length and the STEMI length is high, so the explosive energy tends to travel towards the column's direction, the column distance, then creating either air blocks or fly rocks. So as soon as the explosive energy travels through the STEMI column and tends to reach the surface before the explosive energy traveling through the rock gets to the free phase, then it tends to perform more work at the closer distance to the surface, then projecting some of the rock at the column, the whole column circumference, projecting it to the surface, then creating fly rocks. What makes the explosive energy to travel faster in the STEMI material, in the STEMI column compared to the rock mass is as a result of the condition of the material that is used as the stemming material. We understand that explosive rate of shock wave traveling depends on the sonic velocity. The sonic velocity and the impedance of the material that is the medium through which the shock energy is being traveled through. So the sonic velocity and the impedance of STEMI material tends to be lower compared to that of rock mass. So it tends to travel faster in the rock mass due to the intact, the bond between them. So there is connection within the rock mass, and the rock particles are intact. So the STEMI materials, no matter how compacted they are, the bond within the particles cannot be compared to the rock mass. So it tends, due to the reduction in the impedance of the STEMI column, so the explosive travels slower, just like when it comes in contact with air, which is of very low impedance, then reflects back as a change in phase or change in medium. So the same thing. So to avoid the effect of STEMI in the place of reduction in confinement, which can lead to blow out of the energy or the projection of rock, it's very important that we arrange and design the STEMI length in such a way that it will accommodate proper confinement of the gas energy. And I want to confirm this as been confirmed by Conyard research in 1963 and every other researchers. It has been confirmed and established that stemming affects gas energy and it has no effect on shock energy. Shocking the shock energy have less concern about what the stemming will do, whether the stemming is okay or is not okay. The shock energy tends to perform its function effectively compared to the effect of gas energy. The gas energy, which is defined in the place of the explosion pressure. So if the confinement is reduced, then the explosion pressure tends to lose its efficiency in throwing the rock and causing more of the breakage. So we expect the explosion pressure in the place of the gas energy to be released after the shock wave have traveled and returned, creating microfractures within the rock. So assuming if the STEMI length is not sufficient, then it affects the gas energy, because most of the gas energy, due to the effect that the STEMI length have on it, it tends to allow some of the gas energy to escape towards the weak zone, which the energy finds to be the polar distance. So it tends to escape and reducing the efficiency on the rock in the place of the throw and the casting of the rock that can advance or help the effective breakage of the rock. So that is the effect of stemming on gas energy and the effect of stemming on the breakage of the rock. So how can we ensure that our stemming is okay? One of the factors that will determine maybe your stemming will be okay or not when you are carrying out the blast design is the collar length. That means the length, the left out distance, the left out length, vertical length in the hole that will be filled with the inert material. If the distance or the length is shorter, there's an effect. If it's too much, there's an effect. Too much of stem length, we will definitely reduce the charge density, the powder factor, and the weight of the explosive that will be contained in the rock. And if this is reduced, then you have to produce, you will have more of oversized, more of boulders that will be produced. So that's the effect of maximum effect of SX stemming length. That's effect on blasting them. Effect of inadequate stemming length on blasting is that if you have inadequate, then you tend to expose the environment to an impact of blowout and fly rocks and even ground vibration, because the energy will be closer to the surface, then tends to shift the surface and affect increase the vibration rate and also increase the projection rate of rock to the environment. Also, what can be those factors that we can use to optimize our stemming length? One of the factor is the stemming material that is being used and the stemming, and also the depth and the depth of the stemming material that is being charged, and also the tapping rate, the compression rate. So one of the proposed method of the proposed materials that is being used for stemming is the aggregate that is of high grade. I mean that of high grade of poor sorting materials that have different particle sizes, of which the particle size is ranging from 1/10 of the whole diameter to 1/20 of the whole diameter. Though this material tends to be scarce and it tends to be costly, but they have been proved to be of effect in the rate of confinement and in the place of confinement of the hole. Though in most of blasting or mine sites, the drill cutting, I mean the rock materials that is being blown out by the drill fluid, I mean the air during drilling, is used in most quarry, but most researchers have already carried the research and confirmed that the use of highly graded, poor sorted materials in the place of particles, granite aggregates that is of size 1/10 to size 1/20 of the whole diameter tends to perform effectively and tends to ensure proper distribution of the energy. So finally, I'll be concluding with this note that proper stemming will help us to achieve proper good fragmentation, because most of the energy that is being released by the explosive is controlled by the rate of confinement. If the confinement rate is weak towards one zone, so most of the energy will be diverted to that zone, because it's just like a bottle of Coke that is under pressure. As soon as the cover is being released or the cover is weakened, most of the gas energy tends to escape. It's just like the effect of fractures, the effect of existing discontinuity on rocks. The same as effect of poor confinement. If the confinement is poor, the way the coke gas energy will tend to escape through the cap if there's loose or weakness. The same thing, the gas energy from explosive will escape and do more of work, then producing more of boulders due to the high burden that will be on the little gas energy that is left behind. Thank you very much. I'll be releasing this video also on my YouTube, where you can download it of low data. Thank you. Kindly comment and like the video. Thank you very much.